Hi, I hope everyone can hear me. Uh, I am Rajarshi Basu and I have been doing competitive programming for a while. I'll be discussing the lunchtime problems today, what I'm saying. Anyway, my username on CodeShip is Rajarshi_Basu and on CodeForces it's Resting Rajarshi. I have been to several competitions as well, including this year's IUI where I won a bronze. Anyway, so let's just jump into the problems. Okay, so the easiest problem I guess was Chef in Fantasy League. So firstly, I would like to clarify that before continuing with the discussion, I expect everyone to at least give the problems a read at least once so that there are no confusions as to what the constraints are or what the problem exactly wants. Anyway, I'll still read the statement or the brief of the statements once. So here we have n players and each player can be either a defender or a forward and each player has a price PI. Now you are the coach and you want to buy at least two players, one defender and one forward, and that will make your team complete. So it's also given that the sum of prices of all players in a team must not exceed $100 and the player's chef bought already cost him $S. So how much money do you have left? 100 minus S, right? So using this money, you want to buy two players, one defender, one forward, so that the total cost incurred is minimum. Okay, and the constraints are pretty low. So at most 100 players, total cost is given as 100. Price of players can be also at most 100, right? So okay, so this is pretty simple, I guess. So firstly, you want to check whether there is at least one defender and at least one forward present, right? Because if there is no defender or if there is no forwards, then your team won't be complete. So that's the first check that you should do. Second, now I can buy any defender or any forward, right? But I have to minimize the total cost. So for all the defenders, I want to choose that defender which has the minimum cost, right? And similarly for the same thing for the forward. So let's say you have 5 defenders and you have say 7 forward players and each of the 5 defenders have some cost. I want to take the defender with the minimum cost. Same for the forward players. I have 7 forwards. I want to take the forward player with the minimum cost. Let's say this is the min D is the minimum cost of defender, min F is the minimum cost of the forward player. What is the total cost that I incur? Min D plus min F, right? Now I only have to check whether min D plus min F, that is the total cost incurred, plus S is less than equal to 100 or not, correct? Because S dollars I have already spent and I have total amount of $100. I take the minimum defender, the minimum forward plus S should be less than equal to 100. That was it. So I don't think anyone should have any more problems in this problem at least, right? Okay, so I'll move on to the next problem. Another birthday present, yeah. So this problem is you are given a sequence, right? Sequence is basically an array and an integer k. So you can do a particular type of operation. What is that? Choose any integer I, not like this index I, and choose and then you can swap index I with index I plus k. Okay, so just to show how that would look like, let's say you have this array. Okay, and let's say you have k equal to 2. Okay. K equal to 2. So what does this mean? That you can swap this place, this location with, so this is, let's say, numbering it as, okay, I'll instead use the text, that is easier, I guess. So this is 0, 1, 2, 3, 4, 5, 6, 7. So these are the indices of the array. So I can swap this 0th position with 2, right? So 0 plus 2 is 2. I can then swap this 2 with 4, right? I can swap 4 with 6. Now let's try for another element. So 1, I can swap 1 with 3, 3 with 5, 5 with 7, right? So one of the important conclusions that we can draw is, if I have a number at say 1, I can move that to 1 plus 2 3, 1 plus 2 plus 2 5, 1 plus 2 plus 2 plus 2 7. So I can move it to any number. So let's say if I was at number I, so if I was at index, let's call it j, I can move to any index which can be represented as j plus x into k. So x is any number, right? X is any actually x is any integer. Actually, like x can be negative as well, because let's say I started at 3, right? So 3 can be swapped to 1, so and 3 can be swapped to 5 and 7, right? So as long as j plus x into k is inside our array bounds, I can move to that place, right? Like I can swap consecutively. So what this means is that, even from the diagram, I think it's easy to see, is that the first k minus, like the first k places, okay, so these are the first k places, any number here. So like these are so you cannot exchange anything in the first k places, okay? So let me use another color here. Yeah. And let's say k is equal to 3, okay? So let's say k equal to 3, then inside these first 3 places, you cannot really swap anything in these first 3 places, right? Similarly, in the next 3 places also you cannot swap. Now, what you can do is divide each cell in terms of modulo k, okay? So what do I mean by that? Um, so let's say k was 4. So position 0 becomes 0, right? Position 1 becomes 1, 2 becomes 2, 3 becomes 3. Now 4 again becomes 0, 5 becomes 1, 6 becomes 2, and so on. So I effectively becomes, like you can group I as in the group of I mod k, okay? So if you had say 36, 35, then 35 mod 4 is 3, right? So you would have placed it in accord, like along with 3, 35, let's say some other number, 4 plus 3, 7, all of them will be in the same group. Now, what does this represent? Remember that we had derived this formula, um, like not exactly derived, but like kind of observed, was j plus x into k. Now, if you take mod k, that just means j, right? So effectively, if you are at j, you can move to any other position. Okay, someone is asking if this is for division 1 and 2. This problem is in division 2, I think, not in division 1. Yeah. So since you take j plus x into k mod k, that mod, like that x into k part becomes 0, right? Due to modulus, like properties of modulo. So you are effectively, so what I'm saying is that anything that can be represented at j plus x into k, you can swap it with j, right? And you cannot swap it with any other modulo value. So if you had another number, I plus x into k, right, y, here you cannot really go from this I plus y into k to j plus x into k, correct? Okay, someone is saying you don't get this j plus x into k part. So okay, let me try again. Let me first draw a good array. So this is our array. Weird stuff is happening. Let me just draw. Yeah. Okay, so let's say you are at index 0. Okay, so you are at index 0. This is 0. Now you can, and say k is equal to 3. So you can hop from 0 to 0, 1, 2, 3. Plus you can do another 3, right? Because you can swap these two, and then you can again swap these two, right? So effectively anything that is at position j, it can move to any j plus k, j plus 2 into k, j plus 3 into k, j plus 4 into k. That is why I'm saying it as j plus x into k, where x is any integer. Notice that it can also move backwards, like j minus k, j minus 2k, something like that. Now what I'm saying is that means like some position I and j can be like, you can go from here to there, right? If they have the same modulo k. Because why? You can effectively think of it as so let's say I have 3 into k as an example, and another place I have I plus 5 into k. So you can swap between these two items, right? I mean, it will be a longer process, but you can swap between these two items. So what is the like same thing among these? It's just mod k. If you take mod k, both of them will give I, correct? I obviously I assume that I is less than k here, right? If I was something like, I mean, if I had some I was greater than k, then again you could have, if I was some x plus k, you could have just shifted this k to this side and made this 4, right? So yeah, I hope that part is clear. Anyway, so what do we get from here? Anything that has the same modulo k can be shifted around in between themselves. If two indexes have different modulos when taken like modulo k, they like you cannot shift one item to that, like you cannot move that I to j if I and j have different modulos, right? Because like, I mean, you can only do plus k at a time, and plus k mod k is effectively 0, right? So you are every time you do one operation, you are effectively not changing its modulo value. So even after if you do many swaps and many modulo values, uh, then it's not possible, right? So effectively you have separated your array into k different arrays, right? In between each array you can move anything to anywhere, right? So it's effectively like you have like separated your entire array into k pieces. In each of the k pieces you can sort, you can do anything, right? So our question asks us if the entire array can be sorted, right? So after differentiating it into k arrays, sort each one of them, right? You can sort using swaps, obviously. And then, I mean, you could have sorted using swaps, but we don't care how you sort. It's just possible to be sorted. So you just sort it, and then, okay, someone is asking if duplicate elements are present, then the remainder can be 0, k minus 1 or 1. Duplicate elements, see, I'm not taking modulo of the value at ith index. I'm taking the modulo of the index itself. The value of the index doesn't really matter at this point. Value of the index matters when we sort the entire array, right? So yeah, so what we had basically created is, for this given array, we had k smaller arrays, right? So if k was 3, we had, okay, this is very poor drawing. If k was 3, we would have had 3 arrays like this, correct? Each of length n by k. You sort these 3 arrays, and now, so in the example, let's see. Okay, so in the second example, okay, so let's see the second example. Let me increase the font. So here, what will be our two separate arrays? 1 and 2, 4 and 3. correct? So 1 and 2 is basically at position 0, and at position 2 we have 1 and 2, hence this array. So this basically represents uh, indices that are 0 modulo 2, correct? And the second set represents indexes that are 1 modulo 2. You cannot have any other modulo 2, right? Now you sort the first thing is already sorted, right? You sort the second thing as well, so it becomes 3 comma 4, 3 comma 4, right? Now you place them as they were in the original array. So like 1 and 2 will be like 1 and 2, 3 and 4 will be 1, 3, 2, 4. Make sense? Okay, someone had asked some question. Please don't like copy paste codes in the chat, I guess. Like, I mean, if you have any difficulty, then try to debug on your own. Yeah. So anyway, so it becomes 1, 3, 2, 4, right? And you cannot like swap anything between two different modular values. So this is the best case scenario. If you sort everything in ascending order, you can get, like, this is the best case scenario that you can sort. You cannot do anything else. If this array is not sorted, then there is no other way you could have sorted it, right? So now just check whether the final array is sorted or not. If it is sorted, then all good. It's yes. If it is not sorted, then it's a no, right? Now, as for complexity, separating this into each modulo takes like order and time, right? You have k lists, and each time you like shift to the next modulo, you append that item to the respective list, and uh, then you just sort it, right? So overall, it's like n log n only, because like sorting is n log n. So yeah, okay. So input size is not 10 to the power 9. The number of see, we are only traversing the entire array once. The 10 to the power 9 part, it's only while we are sorting, right, inside each separate array. So that does not affect our complexity, right? I mean, if you had an array which had 10 to elements up to 10 to the power 9, the complexity of sorting is still n log n, right? That is why, yeah. Decreasing sort. Okay, so okay, so there are a few questions here, right? So okay, so I think you have to check for both decreasing and increasing. The problem statement is not clear in that way, I guess. But yeah, it should be both increasing and decreasing, I think. And then, okay, so what are the other questions? Time complexity. In what order do we arrange the sorted subgroups? Okay, so you had so you arrange like you have the sorted subgroups of 0, 1, 2, 3, 4, right? So you take the first element of 0 first of the array, first element of 1, append it, so first element of 2, append it, first element of 3, append it, again go to the next position and append it like that. Did you get how we are rearranging? I think that detail should be like given well in the editorial, like you should be able to get how you arrange in the end. I mean, you don't want to disturb the order bit, like obviously it will be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Yeah, so time complexity is not okay. So someone is asking whether the time complexity is n by k into n log n. That is not the case, right? See, after you have separated it into k groups, rather you had modulo k, right? Huh? You have separated it into k groups. Each group has now n by k elements, right? What is the time to sort n by k elements? It's n by k log n. And you have k groups, so it's k into n by k log n. It's actually log n by k, but doesn't make much of a difference, so that k in the first and like in the denominator effectively gets cancelled. uh, yeah, so it's something like we have k groups, right, and sorting each group takes n by k log n by k. So this k and this k gets cancelled. You have n log n by k. Yeah. So I think this problem is also like sufficiently explained, I guess, hopefully. Okay, so these two are the easy problems of the contest. Next is positive MEX. This problem was present in both Division 2 and Division 1. It was the first problem of Division 1, I guess. This is a bit more trickier. Okay, so I'll just go over what MEX means. MEX is minimum excluded element, I think, right? So MEX basically means that if you have a list, say 1, 2, 3, 5, 7. So minimum excluded element is the minimum integer, or rather the minimum natural number that is not present in your list. So if you had 1, 2, 3, 5, 7, 4 is not in your list, so 4 is the max, correct? So the problem asks that you are given an array again. You can take any subsequence. So there is a difference between subsequence and subarray. Subarray is necessarily contiguous, like at least like we use it as a convention that subarray is contiguous. Subsequence can be like any set of elements basically. So for subarray, if you have an array of indexes 1 to n, for subarray you can choose 3, 4, 5, 6, 7. You cannot choose 3, 4, 7, 8. It has to be contiguous. For subsequence, there is no such restriction. You can choose 2, 5, 7, 8. You can obviously choose 2, 3, 4, 5, but yeah, there's no such restrictions. So okay, so yeah, so in this problem you are asked to find for each subsequence, you find the max of that subsequence, right? So if you had, so let's go to one. Okay, so the examples, I think I'll give you one example. Let's say you have 1, 2, 5, 7, 6. So now here from this array, you want to find, you take the subsequence s as, you take the subsequence as, so let me just give the index numbers as well so that it's clearer. You take the indexes 1, 3, 5, 7. Okay, so what do these numbers correspond to? This corresponds to 1, 2, 3, and 5. Okay, so these are basically the indexes, and these are the actual numbers. Fine. Now what is the max of this s thing? You have 1, you have 2, you have 3, you do not have 4, right? So 4 is the max. Okay, so 4 is the max. Now the problem is choose all subsequences, find all subsequent, and then each of the subsequences has a definite max value, right? Now let's say you had all the numbers from 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8. Then the max is just 9, correct? So yeah, so find all the max values and then just add them up. Okay, 1, 0 something. Yeah, so this f function is basically just the max, and you have to print sum of f. So we can see that the like n is up to 10 to the power 5, right? So what is the most direct solution that comes to our mind? It's generate all subsequences. How many subsequences can there be? 2 to the power n, right? And like if you don't want to include the empty set, then it's 2 to the power n minus 1, correct? So since like subsequence is basically any set of indexes, that's why it's 2 to the power n. Now, obviously, anything of that sort will not work here, right? N is just too large. Okay, so now someone asked in the chat, how do we know that this is not a DP problem, or how do we like kind of go about, right? So what, like a very common technique in actually a lot of problems, but especially in these type of problems where you have to find the some property of all subsequences and then add that property, or say multiply that property, right? So one thing is, instead of enumerating the subsequences, enumerating as in listing the subsequences, okay, I find all the subsequences, I generate all the values, and then I add them up. A better way is rather think that, let's say I have 10 subsequences, 5 of them give a value of 3. So instead of generating all 5 of them and then getting the value 3, I can argue that I want to count how many of them give the value 3. Okay, so it's like I'm fixing a max value, and I'm saying that, okay, how many subsequences of my array give this particular max value. Okay, so this type of reasoning is like common in a lot of problems of this type, key find all sets or all subsequences, where you want to, like, you have some function over the subsequence that gives a certain value, you want to add them up over all subsets or all sets or something like that. So instead of fixing on the subsequence, you fix on the value that you get and count how many subsequences give those values. So now our question is, what else can we observe here, right? So one thing is that if you have n numbers, your like the bound on AI here is 10 to the power 9, right? So you may think that, okay, my max value can be up to 10 to the power 9. And obviously we cannot iterate over 10 to the power 9 values, right? So that is not the case here. Why? Because a max, like if you have n values, your max value can be at most n plus 1, right? Because for a number x to be the max of a sequence or a set, all the numbers 1 to x minus 1 has to be present. So let's say you have some number 10 to the power 6 as the max value, right? Obviously you don't have 10 to the power 6 numbers before you, because total number of numbers present is 10 to the power 5 at most. Hence, like, you cannot attain that max in any scenario. So that is why the maximum max value that you can get is 10 to the power, or rather in terms of n, it's just n or n plus 1, because if you have all the items 1 to n, your max will be n plus 1, right? Okay, so this is the first observation. That means it is indeed possible to iterate over the individual max values if we can only count how many subsequences give that max value, right? So that is our problem now. So I want to just find out how many subsequences give a particular max value. Okay. Uh, so again, let's go to the definition of max. For a particular number x to be the max of a subsequence, we need to have one occurrence, at least one occurrence, could be more, of all the numbers 1, 2, 3, 4, 5, 6, 7 up till x, right? And then x cannot be present, okay? Because if x is present in the sequence, then obviously it cannot be max, right? And then anything above x, it can be present or it may not be present. Okay, so someone asked, do we need to generate all the subsequence? So no, that is what I'm explaining, that you don't need to generate all the subsequences. You think that in your mind, you think that, okay, so let's say this was the max value of a subsequence, then how many such subsequences can we have? So for that, what all observations you have, you need to have 1 to x minus 1 in your subsequence, you cannot have x in your subsequence, and anything greater than x you may or may not have. Now, how do we calculate the number of such subsequences? Well, each number I that is less than x, so this comes directly from our observation, right? Each number I that is less than x, you need to have one or more than one occurrence, right? And so how do we calculate how many subsequences are there such that each number from 1 to x, or rather 1 to x minus 1, has one or more than one occurrences? So first, what we can do is we can count the frequency of each number, right? Okay, so we can count the frequency of each number, right? Now notice that frequency, like the numbers can be up to 10 to the power 9. But okay, so with example, okay, some like, okay, I'll just give an example to, let's see if there's a good example here. 1 to 1. let's say you have this example 1 1. So I'm just giving the list in a sorted order because for subsequences it generally doesn't matter whether what order the individual elements in the list is, right? 3 3 3 4 and 5. Let's say your sequence is like this. Okay, this is your original sequence. Now let's say you want to count how many subsequences have the max of 4. Okay, so you want to count how many subsequences have the max have max equal to 4, right? So this is what you want to count. Now you want to, so how can you count this? So first generate a kind of a frequency table for each of the elements, right? Okay, so now let's say the frequency of 1 is 2, frequency of 2 is also 2, I guess. Yeah, frequency of 3 is equal to 1 2 3 3, frequency of 4 equal to again 3, frequency of 5 equal to 5. Now let's say just for arguments, oh sorry, yeah, sorry, it's 1. Oops. So let's say for argument's sake you had some number like 10 to the power 9 here, right? Now frequency of 10 to the power 9, you would have set it to 1, right? But for a frequency array you cannot have an array of length of 10 to the power 9, right? One alternative is you can use a map, but it's not like, maps are usually not recommended in like any kind of problems, right? So remember how any max value cannot be more than n plus 1. That means any value that you have above n plus 1 are all the same to us. If you have n plus 3, you have n plus 4, n plus 5, all the values are like equivalent to us, right? So if you have any number that is greater than n plus 1, just like reduce it to n plus 2, let's say. Okay, so here n is 1 2 3 4 5 6 7 8 9 10 11 12, right? So 12, you just say that 10 to the power 9 and 14, they are basically the same. Okay, so maps aren't recommended in the sense that maps introduce an additional log and factor, right? And you can do like stuff like suffix sums on arrays that are a bit harder to do on maps. So like recommended in that sense, I was saying. Yeah. Anyway, so yeah, I mean, obviously there are problems that will require maps, but okay, so anyway, I hope this is clear why anything greater than n plus 2 are all the same, because when you are calculating max, you don't actually need the exact value that is greater than x, right? You need how many values can be there. So max can't be more than n plus 1. So anything above n plus 1, it's all the same. So this is just like f of 14 is equal to 1. So let's say we want to calculate what max equal to 4, correct? So I know that at least 1 1 should be there, at least 1 2 should be there, at least 1 3 should be there, right? It could be more. So how many subsets, like um so you can take like one occurrence of 1, you can take 2 occurrence of 1, you can take 3 occurrence of 1, you can take any number of occurrences of 1, right? So what is the way you do that? How many, so it's effectively how many ones you take, how many ways can you take number of ones such that its occurrence is greater than 1. It's basically, if you have, let's say, k ones, you basically do 2 to the power k minus 1, right? I hope this is clear. If f of 1 was 2, you would have done 2 to the power k minus 1. These many ways you can choose number of ones, at least, so that at least there is at least one occurrence. 2 to the power k would have meant that you are taking 0 ones as a possibility, but that is not the case. Like, we won't allow that possibility. Yeah. So here it is 2, right? So I do 2 to the power 2 minus 1. So I can, so how many ones I take? This is the number of possibilities, right? Number of possibilities of 1. Similarly, for 2, I need at least 1 2, but I can have as many 2s as I want, as long as it's at least 1. So again, the same thing. For 3, again, it's like here I have 2 to the power 3 minus 1, right? Because I have 3 occurrences. I can take any number of occurrences. Acha, so now you might, so one question that you might have is, I can take either 1 occurrence of 3, 2 occurrence of 3, 3 occurrence of 3. So isn't that 1 plus 1 plus 1, like 3 types of things I can do? Well, in a subsequence, not only are the items required, right? Not only are how many number of 3s you take, also which indexes you take are important, right? Because subsequents are defined by which all indexes you take. So if you take, say here, if you take this 3 and this 3, if you take these two 3s, this is different than taking this 3 and this 3, correct? Like if you take the first and third 3, it's different from first and second 3. That's what I, so hence essentially it's like you have, let's say 3 occurrences of 3, then you have 3 indexes where there are 3. You want to take a subset of those indexes in your sequence such that there is at least one element. That is why it's like 2 to the power k, because if you had k elements, that's why if you had like k indexes where 3 is placed, you want to take any subset of that, of those k indexes. That is why it's 2 to the power k, excluding null set. So because null set as in empty set, that means you are not taking any index of 3 whatsoever, but that is not allowed, right? You have to take at least 1. That's like the condition that for 4 to be the max. I hope it's clear. If it's not clear, you can write in the chat. Maybe I will try to take on it again. Yeah, exactly. So if you had taken 0 occurrences of 3, 3 itself would have become the max, right? Because but we are calculating for max equal to 4. Does anyone have any doubts till now? You can press on that yes no poll. I think, like, if you have any doubts, press yes, otherwise no. Okay. Okay. Let me try to explain it once again. That will be helpful. Yeah. So instead of yeah. So let me just name these indexes as well. 0, 1, 2, 3. 4, 5, 6, 7. So these are the array indexes. Okay, the above the array. So you want at least one index such that a of I is 3, right? You want at least one of them. You can have 2 of them, you can have 3 of them. So here the indexes 4, 5 and 6 all have the values 3, right? So you can take any subset of those indexes. How many subsets of 3 indexes are there? 2 to the power 3. If there were k occurrences, how many subset of k indexes are there? 2 to the power k. But you cannot take the empty set, right? Because 2 to the power k also includes taking nothing. So you have to take at least one. One of those indexes where 3 is located, you have to take at least one of them. That is why that 2 to the power k minus 1, right? I need at least one of everything that is less than 4. Otherwise, 4 wouldn't have been the max. The thing that had 0 occurrences would have been the max. Is this clear now, Aditya? Yeah. Okay. So now, and I cannot take anything that has index, like that have any index I that has a of I is equal to 4, right? Because then again, not max. So, and then anything above 4, 5, 6, 7, 15, 17, anything, it does not really matter. So let's say I have m values that are greater than 4. We take any 2 to the power m subset of those indexes. So like when I say m values, I mean m indexes where a of I is greater than 4. 5 and okay, someone is asking why are we not considering that 5 and 14 may or may not exist. So I am getting to that part, right? Till now I had been considering everything that is less than 4. 4 cannot exist. Anything greater than 5 may or may not exist. So okay, so someone is also asking how did you store the index when there would be duplicates? You don't really need to store the indexes. You just need to know how many occurrences are there. Correct. Like if you have k occurrences, it does not matter whether the occurrences are at index 1, 3, 7 or 2, 5, 6, as long as there are k occurrences of 3. Uh, I hope that is clear. Okay, so stuff that is above 4. So if I add k indexes, or rather let's take another variable. If I add m indexes, where each I that is belonging to those m indexes, where a of I is greater than 4, that means I can either take that element or not take that element, right? Because anything above 4 does not make any difference. Like 4 will always be the max. So how many possibilities are there? 2 to the power m, right? So again, in combinatorics, how do we multiply, like how do we calculate the total number of possibilities or total number of sequences? We multiply all the possibilities, right? So so let's say I had k1 occurrences of 2, I had k2 occurrences of, sorry, k1 occurrences of 1, k2 occurrences of 2, k3 occurrences of 3, and km occurrences of anything greater than 4. Okay, note that I have exactly 0 occurrences of 4. I don't want to take any 4s, right? So what is the total number of subsequences that are possible now that I have maintained all these conditions? It's 2 to the power k1 minus 1 into 2 to the power k2 minus 1 into 2 to the power k3 minus 1, and so on. Okay, so what is special about 4 is, see, if I start like considering subsequences where 4 is present, obviously you cannot have max as 4, right? I mean, if 4 is present in your subsequence, we cannot have max, right? Okay, so the example that I'm choosing here, oh, okay, so did you ask about since what I chose as the example as 4? I mean, there's nothing special. I'm just showing a dry run of how we are doing. That's it. Yeah, so you have to do this for all I, like, okay, so I'm getting there. So for k equal to 4, sorry, max equal to 4, this is our calculation, right? So I'm taking 2 to the power k1 minus 1, 2 to the power k2 minus 2, k2 minus 1, 2 to the power k3 minus 1 into 2 to the power km minus 1. Km is basically number of indexes or number of occurrences of elements that are greater than 4. So km means everything that is greater than 4. Km is not like mth index. It's, I'm just saying that km means all occurrences that are greater than 4, kind of. So this is the total number of subsequences. Okay, yeah, so this should be actually 2 to the power km. My bad. Sorry about that. Okay, so this is the number of possibilities, the number of subsequences that we can have, that has k, that has max equal to 4, right? That has at least one occurrence of 1, that has at least one occurrence of 2, that has at least one occurrence of 3, and that has any number of occurrences of stuff that is greater than 4, right? So this is for max equal to 4. We need to compute this for all 1 to n plus 1, for all max equal to 1 to n plus 1, right? So like that was essentially the problem. Okay, so I hope everyone knows how to calculate 2 to the power k1, right, or k2, k3, k4, stuff like that. So it's using binary exponentiation, right? So for if you guys want to learn more about binary exponentiation or like need some help, these are like two tutorials I'm like posting on the group. Okay, so to everyone in meeting, so this is one. Yeah, it's basically modular exponentiation. Yeah, right. So these are like, one is a blog link, one is a YouTube link. that should be enough, right? So how long does this computation take, right? So note that this 2 to the power k1 minus 1 that you are doing. So let's say if I write some pseudocode, let's open this Sublime. I hope everyone can see this Sublime text, right? Okay, someone is asking m is f of 5 plus f of 14. Yeah, m is f of 5 plus f of 14, correct? Yes, you are correct. So that is basically here, then f of 5 plus f of 14 is just 2, right? So it's 2 to the power 2. Yeah. So let's try writing some pseudocode, right? Oops. So what I'm doing is, for all I from max cannot be 0, can it? No. So for all I from 1 to n plus 1, right? So here what I'm doing is, I'm rather for all, let's not call it I, let's call it max, right? So I'm fixing our max to be this variable max, just for clarity. Okay, so now what do I have to do? I essentially have to take a like a multiplication thing, right? P equal to 1, and then for all I less than max, strictly less than max, I do P into equal to 2 to the k minus 1, correct? That k as in, let's say you have the occurrences of each I, right? You have listed them in f of I, okay? F of I represents number of occurrences of I in our array A. Okay, A is our like original array. And so k here, what is k? K is effectively f of I, right? Number of occurrences, you take any subset of those occurrences, do minus 1. This is just what we talked about, right? Okay, and then let's say our variable m, right, or km as in the code. Okay, so one thing to note is f of I is not a map. F of I, we are using an array. For maps, it induces an extra log n factor, so maps are not like, don't use maps here and there. Okay, so km, as we talked about, km is basically sum of, like, uh, let's put it to 0. I'll just do the pseudocode again then. For all j greater than max, right? Sum, rather km plus equal f of j. Okay. So what does this mean? Km is basically sum of all items, the sum of the occurrences of all items that are greater than max, right? So that is what we were talking about in km only, right? So in our example, it was f of 5 plus f of 14, right? Okay, so now what do we do? We have already like accounted for all possibilities of things that are less than max. Now for greater than max, I just do p into equal to 2 to the power km, but that's it. Because anything that is greater than max, we can either include or not include, right? We don't need one occurrence of stuff. We can have 0 occurrences. So null set is possible. So yeah, this is basically it. Now, what's the complexity? Uh, okay, so someone is asking, if it is greater than n, then we can simply ignore it. No, we cannot ignore it, right? Because if say some element is like 3n, okay, so if n was like 12, if some element is 36, it cannot be the max value. But let's say you have all the subsequences without 36, right? Now in all of the subsequences you can put a 36 at the back. Those are still valid subsequences, right? Because you have 36 in your array, and all of those max values will not be changed, obviously. So that's why for stuff that is greater than max, you can either include it or not include it. It does not matter how big it is, or if it is greater than n or lesser than n. It does not matter as long as it is greater than your max value. I hope that is clear. Yeah. Okay, so what is the complexity of the pseudocode as I wrote it? We are iterating over n, right? Max value can be from 1 to n. And then we are also iterating over all the values of I, all the values of I that is less than max. So it becomes, so these parts are also order n, right? And our outer loop was obviously order n. So it becomes n squared, right? But n squared is not our optimal, like we don't want n squared, right? How do we improve? See, these values that we are multiplying, or rather that we are adding, these can be done using prefix sums. So in particular, this thing can be done using prefix sum. This thing can be done using prefix multiplication, maybe, whatever you call it. Anyway, it's like, yeah, prefix sum, prefix multiplication, that logic will essentially ensure that you don't loop over all the values. You maintain that prefix sum or prefix multiplication thing, and so effectively it becomes order 1, right? Yeah. So just use prefix sums and prefix multiplications. Now, one question in the editorial section that I found, that was, what if in our case, right, in our array that we were discussing, our, let's say 14 was not here, okay? Let's say 14 was not here. So here we have n up to 10, right? So that means our max value can be up to 10 while in our loop. But max value can never be 10, right? Max value can be at most 6. So what's happening? So see, when we are computing max for 10, we are essentially getting 0 only, right? Because we won't get the occurrences of 6 or 7 or 8 or 9 that we required in our 10. So effectively, when we are calculating the number of possibilities in this part, when we go to f of 6, right, it is 0, right? So 2 to the power 0 is equal to 1. We are subtracting 1 from there, so it's essentially 0. So our p thing here that we are keeping track of, this p becomes 0 when we, as soon as we reach something that is the maximum possible max you can imagine it as, right? So yeah, that was one thing that I wanted to discuss. Yeah, so I hope any other doubts in this problem. Okay, someone wants to ask, how will you enumerate the occurrences into the array fi if the input was something like 1, 5, 5, 10? Then f of 1 is 1, f of 2 is 0, f of 3 is 0, f of 4 is 0, f of 5 is 2, f of 6 is 0, and so on. Again, f of 10 is 1. Again, remember that we have to shrink everything, right? Because if anything's value is greater than n plus 2, you replace it with n plus 2, as it does not make any difference to our problem solving like approach. Yeah. So this was the third problem, I guess. And the last problem that we will be discussing is a bit on the, again, on the higher side. The problem is triangle query. Yes. So okay, someone is saying that whether it should have been replaced by n plus 1. I mean, see, for 1 to n, no, it should have been n plus 2 only, because if you have n elements, so say you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to n. Okay, yeah, it can be replaced by n plus 1, because if you have 1 to n, then obviously there is nothing greater than n plus 2. And if there is anything greater than n plus 2, that means there is a something that is not, like, your max can never be n plus 1 then. So you can just remove with n plus 1. That is not much of a worry, like just remove it with n plus, like replace it with n plus 5. No one, like, does not really matter. The only reason it mattered was so that the frequency array is not of size 10 to the power 9, it's of the size 10 to the power 5, or rather of the size order n. Okay, so let's go to this uh, triangle query problem. So I'll explain this using the diagram because the diagram is very well drawn. So what we want is, we are given certain points in our 2D space, right? So x comma y pairs. Now you are given this sort of a triangle. So how it is defined in the query, you are given the left endpoint, you are given the right endpoint, and you know that these angles, okay, the base angles are 45-degree and the above angle is 90-degree. It's not actually given that the base angles are 45-degree. The statement says that the one of the angles is 90-degree and it's an isosceles triangle. So from that you can derive that, okay, the base angles are 45-degree. And now you have to count for each triangle how many points lie inside that triangle. Okay, so when I see this problem, the first thing that comes to my mind is obviously number of queries, number like n and q, right? Number of points, number of queries is very big, is 10 to the power 6. That means nothing of the sort of square root decomposition will also work. Okay, so usually we think that I mean, okay, so the very first thing that comes to my mind, it's obviously some data structure problem, right? Because it's a very common thing in data structures that you have some 2D points, right? Even if you don't actually have them as 2D points, you can sometimes transform them into 2D points, and you try to find number of points in a certain region. The problem also is kind of like that, you have some given 2D points and you want to find number of points in a certain region. So that is why like the first thing that should come to your mind when you see such kind of problems, it needs some kind of data structure. Okay, so one thing I'll link, or rather I'll give, is like this construct that I was saying, that yes, so maybe this blog might help you, like this post. Okay, so here, like, I kind of talk more about how we can, like, convert certain problems into these problems of 2D points, and then it reduces to counting number of 2D points inside a rectangle or inside a triangle, something like that. Yeah. So where was my problem? I got lost. Yep, yeah. So often what we kind of try is, instead of directly jumping into some data structure, like uh, let's say like a segment tree or something, we try to see that if square root decomposition is possible, because square root decomposition is like almost always your like complexity gets worse, but it's easier to implement and it's easier to think about. But with 10 to the power 6, you cannot have anything like n root n complexity, right? That's just too much to work around. Like, okay, so that means we need to have something better. Now, let me draw this diagram, and then we will see what we can observe from the diagram. So note that the angle is given as 45-degree, and that's pretty specific, right? It's not some any random triangle. The base angles are not any random angles. 45-degree means the lines have a slope of 1. So let me draw a diagram, right? And say these are my red points. Okay. And then these are, let's say this is my triangle. Okay. Now this coordinate here, I'll name it as a comma 0. Yep. Coordinate geometry, yes. And this triangle is b comma 0, right? And what's the point here? Here it is effectively, what is it? Um, it's something at least a plus b by 2 for the x coordinate, and for the y coordinate it's b minus a by 2, I guess. B minus a by 2, something like this. Okay. Yeah, something like this. So okay, so one very one trick in these sorts of problems, see, this by 2 thing is kind of bad, right? Because if a plus b is odd, you have some fractional value, and double precision is always a bit messy. So just multiply all the coordinates by 2. That effectively just kind of stretches your diagram in like twice as large. It does not mess around with what point was inside a triangle. It does not become, it does not get outside it. It's just scaling the thing. What's the benefit? Everything is like an odd, like even integer, right? Even integers get even, odd integers also become even. So when you are adding, subtracting, dividing by 2, you don't have to worry about fractional values. So that's the first, like, what to say, transformation that you can do to your points and to your triangles. That's usually helpful from an implementation perspective, obviously. um, yeah. Okay. Now this kind of a triangle is kind of hard to work with, right? Because we have, see, slanting slopes are worse, right, than straight lines, or yeah, so like anything parallel to x-axis or anything parallel to y-axis, those are easy to work with, right? Because had you sorted your array with x or y, then there's a specific region, right of it is right of it, left of it is left of the line. Slanting regions are more difficult to work with. Like, you cannot just sort based on x and y and figure ki, okay, this does not lie in my region. So divide this triangle into 2 triangles, right? Because why not? So divide this triangle into 2 triangles. So something like this. And so now you have one left triangle and one right triangle, I think. Even in the editorial, it uses a similar kind of a language. And now if you just count how many points lie on the right triangle, how many points lie on the left triangle, add them up, you get the total number of points. Note that points that lie exactly on this boundary, you might overcount them twice. So make sure you don't do that. You can just like do like count in each triangle and then just subtract anything that has x value as this specific, x value as a plus b by 2, and y value that is less than equal to b minus a by 2, to like avoid that overcounting thing, right? Like subtract one occurrence of all of those. Yeah. So we have reduced our problem, right, to counting something that is inside just one right angle triangle. Right angle triangle that has the isosceles right angle triangle, right? All the angles are 45 degrees. Yep. So let us simplify our diagram. Okay. So this is our coordinate plane. Let's say, oops, what happened? That was bad. Let's say your triangle is something like this. And okay, for what hidden purposes, I will extend this line a bit, right? And then your points are like, here there is a point, here there is a point, here there is a point, here there are 2 points, right? Now Each of these points have an x and y value, correct? Each of these points has an x and y value. So this is x1 comma y1. It's not writing. Why is it not writing? X1 comma y1. A point like this here, this point here has, let's say, x2 comma y2. Okay. Now, okay, so we will mark some more points. This is a comma 0. This is, wait, this is b comma 0, and then this above vertex, what is this? This is b comma b minus a, right? Because it's isosceles, so b minus a is the bottom part, b minus a is also the vertical part. Okay, so this is just simple coordinate geometry, yes. Now we want to derive a condition such that our point, so that we can figure out which point lies inside our triangle and which point does not lie inside our triangle. So what's the brute force approach here? So we always try to figure out a brute force approach, preferably something that is n square, and then we try to figure out how do we optimize it to n log n or n log square n using some data structure, okay, some magic data structure. So the data structure is just for optimizing it. It's not actually inside the logic per se. So yeah, so I'll get to what I mean in a minute. So what kind of a thing can we have here? So let me just shift this screen here so that it's visible. And then let me okay, so what do we do? Now note that for a point to lie inside, so we are considering all triangles of this left triangle kind of thing, right? The slope is kind of positive, like the hypotenuse slope is positive. The other triangle was the opposite, like the right side one. So we are for now considering everything that is the left side one. So for a point, let's say x comma y, what are the conditions that it needs to satisfy? So one possible thing is that if we know that if we know what all conditions it will have to satisfy to lie inside the triangle, the most obvious brute force approach here is consider all triangles, consider all points, and just see for every point whether it lies inside the triangle, right? So what's the first condition? The x coordinate, x value has to lie within a and b, right? This is the first condition because these points, right? These points a and b, it has to lie within them, right? So basically it means that it has to lie within this section. Don't mind anything that is below this line, and this section, correct? What all conditions do we need to have? Second criteria is, let's consider x1. So remember how I told that it's a special kind of a triangle so that the hypotenuse slope is exactly equal to 1. So what does that mean? That means that when I do x1 minus a, correct? So I am considering everything relative to this point. I am transforming all my coordinates relative to this endpoint. Sorry, this endpoint, okay? Okay. So obviously now our y coordinates won't change, right? Like our endpoint is on the x-axis. So now if I consider with this endpoint, for a point to be inside our triangle, that means the slope of that point to origin, right, is less than 1 or less than equal to 1. So how do we write slope? We write slope is equal to y1 by x1 minus a, right? This is slope, right? Yeah. Has to be less than equal to 1 because 1 is our hypotenuse line, right? Remember 45 degree means slope of 1. Yeah, so that is essentially what we are using here, right? So our slope equal to one line is basically this line, this hypotenuse line. This is our slope equal to one line. Anything that has slope, like, so for example, this is a valid point, right? This has slope less than 1. That means it's valid. Okay. So let's try to rearrange this formula, correct? So now these are the two only conditions that we require, right? We require that the point lies between these two within this section, and we need that all the points must have slope less than 1 for it to be inside the triangle. Okay. So at this point, you could have just, if for an n square solution, you could have just looked over all the triangles, right? And then checked for all the points, whether if that point was inside the triangle, you increase the counter. If it is not, don't do anything. Now, anything that I do with the left triangle, it's kind of symmetrical with the right triangle, right? You can derive the equations on your own at that time. So there the slope won't be 1, it will be actually be -1, correct? So I will explain only using this left kind of a triangle and not with the right kind of a triangle. It's try to figure it out by yourself. It's obviously given in the editorial as well. But yeah, it's more or less symmetric. So if you get this part, you will get that part. Okay, so someone is asking why are the coordinates of the upper vertices b comma b minus a, as I had written here, and not what I had written earlier. So see, I am not, so there initially, okay, so I should have mentioned this earlier, I guess. Initially we had this sort of a triangle, and I had named this point and this point as a comma b, right? Now I have this triangle, I am considering the left half only, and here I am naming this point as a and this point as b. Okay, this point, this is not b, so this I kind of changed the notation here a bit, so that previous b in the previous image is not the b that we are working with right now. Yeah, so hope that clears it up. Yeah, so if this coordinate is b, right, this coordinate is b, this coordinate is a, then it's just simple geometry that the upper coordinate is b comma b minus a. Okay, so how do we proceed? Okay, so yes, you do have to multiply by 2. Okay, so someone asked that should we still multiply by 2 or not, because here we don't see any fractional values. See, this b value that I am taking here now, this is not the input b value, right? This b value is actually the midpoint of a and b, so that this b is actually a plus b by 2 itself, right? So unless you multiply by 2, this b coordinate itself would be fractional in some cases. uh, okay, I'll just clarify this point quickly once again. This was our triangle initially, right? I had named this point as a, I had named this point as b, correct? Now let's say we drop this perpendicular, right? How we had segmented the triangle into two parts. Let's call this position as C. Okay, for now, let's call it C. C is a plus b by 2, right? Now here in this triangle, I am just renaming C as b uh, just for notation. Like this b is actually not the original b. I mean, if it helps, you can think of it actually as C. Like every b that I mentioned from now onwards is actually a C. It's the midpoint of a and b. But yeah, so you still have to multiply everything by 2 so that you don't get fractional stuff, right? So yeah, I hope this clears it up. So the brute force n square solution is hopefully clear to everyone. Okay, so someone asked that why are you considering. Okay, so there are a couple of questions I'll try to answer. Why am I considering only the first half? Okay, so see, in our original triangle, we had two slanting slopes, right? So as I mentioned, slanting slopes are bad. It's very difficult to handle slanting slopes because uh, whenever there is a slope, there is no definite order, kind of. It's very hard to determine what is above the slope, what is below the slope. If you have some vertical line, it's very easy to know what's to the left of the vertical line to what's to the right of the vertical line. It's just you just check the x coordinate. For horizontal for slanting lines, it's more difficult, right? Now, instead of trying to figure out for two different slanting lines, I try to simplify my problem where I have triangles with only one uh, slanting line and two vertical and horizontal lines. So that's why I divided into two different segments. It shouldn't be, Rohan says that it shouldn't be fractional because it's an isosceles triangle. No, because uh, the isosceles triangle can be like 3, 0, 5, 6, 0, like the bottom parts. And when you take the average, it's like 4.5. The midpoint is 4.5 on the x-axis. So it will be fractional. Yeah. So okay, so the n square part is clear, right? For every triangle, we check every point, increase counter, that's it, using these two conditions, right? Now, my goal here is, see, I have to iterate over all the triangles. I cannot escape doing that. What I can optimize is, instead of iterating over all the points, is there any way to ensure that all, like both of these conditions are getting checked together very fast? So let me rewrite formula 2. Okay. So cross multiply. What do you get by cross multiply? Okay, so I'm using x1 and y1 here for some reason. So by cross multiplying, I get less than equal to x minus a, right? Now, again, this condition is equivalent to condition 2, right? 3 and 2 are equivalent. Okay, 2 is equivalent to 3. Again, it's still very hard to determine why, like condition 3, right? Because on both sides of the equality, you have something that is a property of that point, and you cannot really query into a data structure with a property of a point, because that property itself varies across the points, kind of, if you get what I'm saying. So what do we usually do? We try to get all the point specific properties, like all the properties that vary according to different points, and combine them together. So here, how do I do that? I just say a is less than equal to x minus y, right? Again, 4 is equivalent to 3 is equivalent to 2, right? I just shifted around the terms. So let me once check whether I'm doing everything correct, right? The editorial has these formulas, I guess. Yeah, good. I'm doing everything right. Yeah, so a is less than equal to x minus y. Now, if I check condition 1 and condition 4, then also we can check whether that point belongs to the particular triangle, right? But now see, this is fun because instead of having two distinct properties of the points, we now have just one property, right? If we had z equal to x minus y, this z value is maybe or may not be unique for all the points, but it is a property of all the points, and I just need to check how many z values are greater than a. Correct? This is all that I need to check. So do we know of any data structure where we can insert some numbers and we can check how many numbers are greater than a? If we have any such data structure, then we can easily find all the elements. So all the elements that satisfy only condition 2, right? We still have to worry about condition 1 because that data structure is still not seeing whether condition 1 is satisfied or not. It shouldn't be fractional. No, it can be fractional. You just work out the details for the fractional thing. Okay, sorry. That's an old comment or what? My bad. Yeah. So we still need to check the first condition. Correct. Okay. So the right half, we are not done with the left half yet. We will worry about the right half later. Yeah. So well, for the second condition, if we had a set of point that followed the first condition, we could have checked for the second condition using some magic. Let's say our data structure, we don't know what data structure we will use, but let's say that data structure could do it fast enough. Okay, So like often when you have to check a certain like a few criteria, so what I do is if I have a problem and as a sub problem I have to check, okay, so I need to count certain things which satisfy this condition. I just assume that, okay, let's say I can do it very fast. Now can I proceed from there? Okay, so here also let's say we can enforce condition 4, or we can find how many points satisfy condition 4, as long as they satisfy condition 1, obviously. And let's say we can do it very fast enough, like very fast. Okay, so does that reduce our problem? Kind of, right? Because okay, so we still have to worry about condition 1. So let's see how we can do condition 1. For condition 1, I want to reduce one of these constraints. Okay, instead of a less than equal to x less than equal to b, I'm just saying it's enough to check whether x is less than equal to b. Okay, okay, someone is asking why can we not fuse a minus a, x less than equal to x minus a less than equal to b minus a. So then you would have to check whether then you would have to check. So then what you will have to do is, right, so the point is, what if we in equation 1, or rather in constraint 1, what if we subtracted a from all the sides? So then you would have to check whether x minus a is positive and whether it is lesser than some constant, right? Some b minus a constant. Problem is, for each triangle, a and b are different, right? A and b are properties of the triangle, and x and y are properties of the point. So for each triangle, you would have to update all the x values, correct? So that is kind of bad, right? I mean, then it's not actually a property of the point anymore. It's again a combined property of the point and the triangle in some sense. So it does not really help. Um, yeah. So okay, so here what I can see is we can actually remove that a less than equal to x less than equal to b. May say we can remove the a less than equal to part. Why? See, what are the type of points that we can have? Uh, the points are, I think, given as positive numbers, right? All the points are positive numbers, like all the coordinates. Hence, there can be three types of points. One point is that lies in this portion, okay? One point is that lies in this region, okay? So points like x2 comma y2, so they can never, like they won't lie in the triangle, obviously, and their slopes are greater than 1. Second kind of point is the slopes which are less than 1, but the x values or the y values, rather the x values, are greater than b, and they're the required points, like which satisfy both the conditions. Now in constraint 1, we had also talked about satisfying whether it is in this region, right? In the vertical line I just drew. So it's actually not required for us to check whether the point lies, if the point lies to the left of the vertical line, then its slope is obviously greater than 1. So it does not make sense to check that again, right? So hence we only want to include points, like we only want to enforce that x is less than equal to b, the x is greater than equal to a part, that is getting checked in the second condition itself. If x is less than equal to a, if x is less than a, then the slope is obviously greater than 1, right? So uh, it does, like, you don't need to have a separate condition for that, correct? Now we already know that if we are given a set of points which satisfy condition 1, we had assumed that we can do condition 2, like we can count number of points satisfying condition 2 in like very fast. Okay, so very fast, when I say very fast, it means something that is fast enough. So in this case log n is fast enough, we can, let's say we can do it in log n. We still don't know how, but I am like assuming that we can do it. Okay, uh, so how do we enforce the first constraint? So what we do is we do what is called an offline sweep. Okay, so what is an offline sweep? It's like you, so one thing that you should have seen in this problem is uh, the problem states like all the input is given together, right? So you know all the triangle queries that are going to come. So these problems are called offline problems. Problems where you get a triangle, you find the answer, and then only after that you get the next query. Those are called online problems. Okay, so offline problems are easier in the sense that you already get all the information, right? All the triangle queries that you are get that you are gonna get at the beginning of the thing. Okay, so what you do is for all the left triangles that you have formed, you sort them by their uh, what are those called, altitudes. So in a right angle triangle, it's hypotenuse, base, and altitude, I guess. So you sort them by the altitudes, right, in their x coordinates. So basically you will have something like, let me draw. So you will have things arranged like this, this, this. So you process them in the order. This triangle you will process first, this triangle you will process second, this triangle you will process third. I hope it's clear what order I'm talking about. It's the sorted order of the altitudes. Or by altitudes, I don't mean height. I mean the x coordinates of the altitude. Okay, so it's not like by height I'm sorting, by x coordinates. So what does that ensure? Suppose I'm like as I go rightwards, right? As I like sweep down the plane rightwards. Imagine like a someone sweeping to the right, right? I mean that's how the name is derived. So I start including points in a set. Okay, inside this set, what condition? So when I reach triangle 1, I have already inserted into my set all points that have x values less than equal to b, correct? So that is how I am essentially maintaining constraint 1. When I go to triangle, and remember, nothing that has x value greater than b has been processed yet. No point that has x value greater than b has been processed yet. Only points with less than equal to b have been processed. So in our set, we only contain those values that are less than equal to b, right? Now as we go on to triangle 2, we have again only processed only those points that are less than equal to the b value for triangle 2, right? B2, let's say. We have not processed anything that is greater than b2, like any point whose x value is greater than b2. So this is kind of a neat way of arranging, and then when you get to a certain triangle, you have only processed stuff that have x value less than equal to the triangle's altitude. Um, yeah. So that is the set that you keep maintaining while you process them in sorted order, while you do the offline sweep. Now, this is how you maintain constraint 1. We still have to figure out, we had assumed that we can do part 2 very fast, but we still don't know how, right? So what is effectively part 2? Part 2 is just when you, so what are the operations that you need to support? You have a set of points. I don't mean like STL set, like a set bracket int, like not like that. I mean a collection of points. You know each of the z values for that point, right? Z is basically x minus y, and you want to count number of z values, right, that are greater than some a. So you cannot so what, how do you process that, or how do you support these two queries, that adding a value and checking how many values are greater than a? Well, it's very simple segment trees. It's a very classic problem of segment trees where uh, okay, so there's some question again. Okay, so so I will explain the offline sweep part again. um, just let me tell, like, let me complete the solution once, then I'll go back to it again. Yeah. So it's a very classic problem where you can insert a number into the segment tree, right? And then you can find how many numbers are greater than a. So how do we do that? We maintain the segment tree on a frequency array. Okay, so when we usually talk about segment trees, we are maintaining a segment tree on an array, right? So here we maintain the segment tree on the frequency array. So F0 means how many, like what is the count of 0, F1 what is the count of 1, like just in the previous problem how we had a frequency array, right? So when I add my Z point into the segment tree, I update Zth index, right? So index Z, I update a +1. And when I do the query, I want to check from A to max value. Okay, so segment trees have some max value, right? Z will have some max value. From A to max val, what is the sum of that region? Okay, so that is, so essentially the sum there is equivalent to asking how many points were greater than A, right? Because if a point was greater than A, say A plus 7, then at A plus 7th index, we would have had a +1, right? And that plus 1 would have contributed to our sum that we are querying. So yeah, that is how you do it in a segment tree. It's a very standard problem. You should like maybe go through the editorial ones. I don't think it's mentioned there, but you can go through the code of the setter and tester. Yeah. Okay, so that is a subproblem, and so how we think about that is this is a very known subproblem. Okay, we don't really need to solve it again. Once you have gained some experience, you will know that these are kind of certain very common known subproblems, like maintaining one condition and maintaining two conditions, right? Like let's say if our points had three properties, okay, x, y, and z. I want to say that okay, x has to be in this range, y has to be in this range, z has to be in this range, for, and the ranges are given in as queries into our data structure. So what we can use is like a merge sort tree or a persistent segment tree. If you had two condition, we can just use a segment tree, I think. Stuff like that. So this becomes common after a point. So as you encounter more and more problems, these sub problems where you have to ensure certain criteria are met effectively gets converted into some data structure problem, and you know that okay, I can figure out this data structure later also. I mean, this is doable. I know that it is doable. That's it. Okay, so let me explain the offline sweep part and what I'm doing again. So let me draw a bit of a clearer diagram. Do you guys want me to explain how to do that segment tree part, or do you want to try it on your own? And what I can do is I can try to explain it tomorrow, because tomorrow again we have a session, and I can just if someone doesn't get it, I can try to explain it in tomorrow's session after discussion of the three problems. Yeah, I'll. Okay, so what's about resources for segment trees? Um, I don't think I can give you anything particular that you won't get by Googling. So Google has like lots of resources. At least for segment trees, it's like too many resources, kind of. Okay, I'll still try to. We will try to post some in the editorial if for that particular segment tree version. Okay, so let me give some example of what I'm dealing with offline sweep. So you have some triangles, like we are just considering the left triangles, okay? So this is one left triangle, this is, let's say, another left triangle, this is another left triangle. Okay, so one question someone asked is, for the second condition, we find number of points in segment tree. Yeah. But how are we taking intersection with the points which satisfy the first condition? Yeah. So that is what now the set. So when we are querying for a particular triangle, we have a set of valid points, right? Those set of valid points already already satisfy constraint one. That is why I'm doing the offline sweep, so that the set of points that I'm considering, they already satisfy condition one. And then inside that set of points, inside that set of valid points, I'm checking how many of them satisfy condition two. That is why our segment tree also need to have support that addition query, right? Because as we are doing the offline sweep, we are processing points and we are inserting them into our set of valid points, right? Hence, the segment tree needs to have some update operation as well. So what's the offline sweep? No, we are not making a segment tree for each new query. So think about it like this. Okay, so let me dry run this once, then hopefully it will be clear. So there is, let's say, a point here. There is, let's say, a point here. There is, let's say, a point here. One point here. Okay, so this should do. So first I'm starting from left. I've ordered everything by X. Someone asked me to share some Google Doc link. I'm not using any Google Doc. I'm just using AutoDraw, autodraw.com. So, okay, so we are processing stuff in the order of X coordinates. Okay, both points and the triangles. So first, so now we have, let's say, a set. This is our set. Like, imagine it. This is our, like, a bag that we will include points in. Right. This is our set. And let's say we number these points as 1, 2, 3, and 4. Okay. Now, first we process point 1, right? We are going from left to right. Okay, imagine a line. So imagine that there is this line that is going from left to right. Oops, this is like a right line. So imagine that this line is kind of going from left to right. Okay, we are moving this line like okay, wait a second. Yeah, so we are moving this. We are moving this line kind of like this. Okay, so this is what I mean by an offline sweep. We are sweeping the plane. So this line comes at this point. Okay, so I include this point in my set. Okay, so in my set I write 1, or rather what I include, I don't actually include the point, I include the z value of that point. Okay, so in our segment tree we do a +1. So let's say the z value of point 1 was z1. So in our segment tree we do a +1 to z, the index z1. Now we are again moving this thing, this sweep, this line, and then we reach point 2. Again, we do a +1 at z2 index of our segment tree, right? So we have point 1 and point 2 in our set kind of, and that set is like effectively represented by a segment tree. Okay, so the set that I'm talking about, it's in your mind kind of, and how you are representing that set using a segment tree. Now you are sweeping again, you come to point 3, like include it again. Now you come to this first triangle. Now, what all points do you have in your set right now? Like in your segment tree right now? Only the points that have x value less than equal to b, right? And now you can just query the segment tree to find how many points are inside a certain range, like between a and maxwell, right? So like the segment tree has a z value, the occurrence of z value is +1, right? As I explained. Now you move this line again, you come to this triangle, right? So this the triangles I'm denoting by the x coordinate of the altitudes, the points by the x coordinates. I'm sorting by like in that order. Now you come to this thing, you get, okay, so now also your set only contains anything that is left of my sweep line, right? So it's like, again, same thing. Now you come to point 4, now you include it into your set. Now you again keep sweeping the line. You come to the last triangle. Again, all the points that satisfy the condition are already in your set. That's things that do not satisfy the first condition are not in your set. And then this is like the sweep line. So how do you actually implement it? Once you sort these things, okay, so these are kind of like events. So event 1 is encountering a point, event 2 is encountering a triangle, let's say. So you are basically, you have all the events sorted according to your x-axis. When you do get an event 1, you take the z value and put it into the segment tree. When you get an event 2, you do a query of type 2, right? And this is just basically after you sort your event list, you are basically iterating on the event list, because the event list is sorted by the x coordinate, right? So iterating effectively simulates this sweep line that we were talking about. Correct. Yeah. So this is how you process all the left triangles. The right triangles are symmetrical and similar. Instead of that plus one, like the z value here was x minus y, you do x plus y there, because instead of the plus one, it would have been a minus one. Less than equal to will become greater than equal to. These kind of changes, but effectively the thing is same. And of like for the right triangle, we are doing a sweep line from right to left instead of left to right. But I would suggest that everyone should think about that on their own. I'll not go into depth how we do the right triangle one, because again it's like similar and it's just symmetrical to what we did for the left triangle. Yeah. So any doubts, any questions that you might have in, like, apart from this how to do the segment tree, because you should like try on your own. N log square n was not intended. Okay, someone asked, does Mozart tree TLE? Why does it TLE? So n log square n, see, it's by it's a common like rule of thumb, you might say, that for 10 to the power, when n is 10 to the 6, only n log n or n solution passes. N cube root of n might pass. When n is like 5e, 5 into 10 to the power 5, then also the similar thing. For 2 into 10 to the power 5, usually n log square n is like passes also. It can be n log n, or it might be like n log n into some other log factor. Like you can include 2 log factors at most. For n equal to 10 to the power 5, you usually want n log square n or n root n solutions, right? So these are kind of rule of thumbs that like works. So yeah. So that's why when you see that the constraint is n is equal to 10 to the power 6, you obviously know that okay, merge sort tree n log square n will not work. Let's not try it. Okay. So can I use a simple DS like an array? See, you in an array, if you want to check how many z items are greater than a, it will take order n time, right? I want to, using a segment tree, I can do it in log n. When I say I want to do it in very fast, I mean in log n or something less. Order one is best case scenario, but usually in log n. Order n is just basically same as just checking all the points. Does not help. Yeah. So arrays are not enough. Yeah, okay, so this was like the first 4 problems. Hopefully you got everything. Then I'll stop sharing my